Welcome to our comprehensive tutorial on the DC shunt motor. In this video, we will delve into the basics of the DC shunt motor, explore its components, explain how it operates, and discuss its practical applications in detail. Let's get started. A DC shunt motor is a type of direct current motor where the field windings are connected in parallel, or shunted, with the armature windings. This parallel configuration gives the motor its characteristic of maintaining a constant speed, which makes it ideal for applications where speed control is crucial. Let's begin by looking at the key components of a DC shunt motor. First, we have the armature, also known as the rotor. The armature is the rotating part of the motor and it consists of armature windings and a commutator. The armature windings carry the current that interacts with the magnetic field to produce rotational motion. Next, we have the stator. The stator is the stationary part of the motor and it includes the field windings. The field windings create the magnetic field required for the motor's operation. The field windings, also known as the shunt field, are connected in parallel with the armature. These windings have a high resistance and many turns with a small cross-sectional area. This design allows the field windings to produce a strong magnetic field with a relatively low current. The supply voltage, denoted as V, is the voltage applied to the motor. This voltage powers the motor and drives the current through both the armature and the field windings. The shunt resistance, denoted as RSH, is the resistance of the shunt field windings. This resistance is relatively high to ensure that a small current flows through the field windings, creating a strong magnetic field. The armature resistance, denoted as RA, is the resistance of the armature windings. This resistance is usually low to allow a higher current to flow through the armature, which is necessary for generating torque. The total current, denoted as 𝗗𝗢𝗪𝗡, is the total current supplied to the motor. This current splits into two parts, the armature current, denoted as IA, and the shunt current, denoted as ISH. Understanding the key equations of a DC shunt motor is essential for grasping how it operates. The first important equation is the supply current equation. I total equals IA plus ISH. The total current, 𝗗𝗢𝗪, is the sum of the armature current, IA, and the shunt current, ISH. The shunt current equation is ISH equals V divided by RSH. The shunt current, ISH, is calculated by dividing the supply voltage, V, by the shunt resistance, RSH. The voltage equation is V equals EB plus IARA. The supply voltage, V, is the sum of the back EMF, EB, and the voltage drop across the armature resistance, IARA. Including the brush voltage drop, the equation becomes V equals EB plus IARA minus 2VB. This equation accounts for the voltage drop per brush, denoted as VB. Now, let's understand how a DC shunt motor operates. When the motor starts, the supply voltage, V, is applied across both the armature and the shunt field windings. The shunt field windings generate a magnetic field proportional to the shunt current, ISH. This magnetic field interacts with the armature current to produce torque, causing the armature to rotate. As the armature rotates, it generates a back EMF, denoted as EB. This back EMF opposes the applied voltage and its value increases with the speed of the motor. The back EMF acts as a self-regulating mechanism that limits the armature current and prevents the motor from drawing excessive current. In a steady state, the back EMF nearly equals the supply voltage minus the voltage drop across the armature resistance, RA. This balance ensures that the motor runs at a constant speed, regardless of load variations. Let's talk about torque production in a DC shunt motor. The torque equation is T equals P phi ZIA divided by 2 pi A, where P is the number of poles, phi is the flux per pole, Z is the number of conductors, IA is the armature current, A is the number of parallel paths. The torque produced by the motor is directly proportional to the armature current, IA. As the armature current increases, the torque increases, and vice versa. This relationship allows the motor to provide the necessary torque to drive the load. One of the critical features of a DC shunt motor is its ability to maintain a constant speed. When a load is applied to the motor, the speed decreases. This reduction in speed reduces the back EMF, EB. As a result, the voltage difference across the armature resistance increases, causing an increase in armature current, IA. The increased armature current generates more torque, compensating for the lost speed and allowing the motor to stabilize. Thanks to this self-regulating property, the motor maintains a constant speed regardless of load variations. This characteristic makes DC shunt motors ideal for applications where consistent speed is essential. Finally, let's look at the advantages and applications of DC shunt motors. Advantages of DC shunt motors include constant speed operation, good speed regulation, reliable performance. DC shunt motors are used in a variety of applications requiring constant speed, such as lathes, conveyors, elevators, and other machinery where precise speed control is necessary. To summarize, the DC shunt motor is a versatile and reliable motor that excels in maintaining constant speed, making it invaluable in various industrial applications. We hope this tutorial has helped you understand the fundamentals of the DC shunt motor. Thank you for watching, and don't forget to like, share, and subscribe for more technical tutorials.